came to me and he said, I'm building some machines, but I don't know how to use them. Okay. So I don't know how to optimally design experiments with these machines. Okay, so maybe you can help. And it only took me 4 years before I realized this was a question in a subfield of statistics called optimal design of experiments. So I may not be the sharpest knife in the drawer, but eventually I got there. Okay, it only took 4 years. So that's what I'm going to talk about today. So what I'm going to talk about is more about spectroscopy, not very much math, and a bit of statistics. So what is Raman? What is Raman spectroscopy? So I'll give you the steps and what goes on. So you illuminate a chemical sample with a laser, which is a single frequency, and then the photon is absorbed by molecular bonds. So this is something to do with energy, the energy in the bonds. So the energy in the bonds increases and then it sort of relaxes and the molecule gives off a photon. Now most of the time, the energy of the photon it gives off is the same as the energy that goes in. Okay, that's most of the time. About one time in a million, it gives off a photon of a different frequency, and these photons characterize the chemical bonds, and this led to a Nobel Prize for Raman. And he did this in 1930-something with very primitive equipment, no lasers. So photons given off from that sample have a characteristic distribution of energies, which is a spectrum. And you can think of a spectrum as a probability distribution. In other words, photons are coming randomly off this molecule, and they have different frequencies, different colors, different energies, however you want to talk about it. And the spectrum is the probability distribution of the colors coming off a sample. And the photons with different energies can be separated physically. Okay, like with a prism, So that's no problem. So these things can be spread out, so you can separate physically the things, the different whatever. Okay. So here we go. Here's sort of a schematic of the machine. So here are two samples, not really to scale, unfortunately. But this is the spectrum of acetone, and this is the spectrum of benzene in the current laser thing. So here in acetone, most of the photons have this color, but some of them have this color, and some of them have this color. But in benzene, not most of them, but a lot of them have this color, and a few over here and here. Okay? But they could have any color, but it's most likely to be here for benzene and to be here for acetone. So here's the setup. So you have a laser, comes in, hits a mirror, hits a sample, gets reflected back, hits another mirror, goes through something that removes photons of the input frequency. Okay, I said most of the time it's the input. You don't want to see those photons. So it removes those photons, and then it goes to something like a prism here that separates them. I don't know what this is. So my problem is, what do you put here? So this is a detector, or it's something else. So what do you put here? Okay, so listen, I just want to talk about quantum mechanics, something I don't know anything about, but it implies that quantum mechanics implies that photon emission is modeled extremely accurately by a Poisson process, which is a counting process. N of t is the number of discrete events. And I noticed you had a talk here maybe a week ago that said don't count on Poisson. Okay, but in this case you should. Okay, because it really is. We sampled this thing. So what's the counting process satisfies? It says the number of counts in a period of time h is independent of when you start. If you look at how many counts appear in a bunch of intervals, they're mutually independent if these intervals in time don't overlap. And the probability of having more than one count in this very small time of h, between time t and t plus h, this is little o of h as h tends to 0. So once you have these three properties, you get a Poisson distribution. And the property of the Poisson process is there's a lambda, which is the rate constant. So that's the average number of photons you expect to see per second. Okay, so it's how quickly on average the photons are coming in. So the expected value of the number of photons starting at time s and going to time s plus t is the same as the variance. That's important. So the expectation and the variance are the same, and it's lambda times the length of the interval. Okay, so this is Poisson. I didn't know anything about a Poisson process before I started this. Okay, so here is the experimental setup again. And I'll remind you, the question is, what do we put here? We could put a detector here, or we could put other things there. So everybody has a game, right? When they talk, they have a model. They're assuming things in their head. So I'm trying to write down everything that's in my head here. Okay? So here's our game. We have a list of n known possible chemicals. So think you're in a refinery, okay? And you have a pipe, and you want to know what's going down the pipe. Well, you only have about 10 options. Okay, it's heptane, it's octane, it's propane. It's limited. And you know what the energies of the photons in the spectrum of each of these chemicals are, and you can divide them into little discrete bits. Don't look at this gray behind the. Ignore the gray right now. Anyway, we can divide it into bins, okay, and then and so then we can classify the energy of each photon coming in as to which bin it's in. And what we want to do is we want to estimate the rate. Remember I said each thing has a rate. The rate lambda j at which photons are emitted from chemical Sj. Okay, so if we don't have any photons coming from acetone, then if we have a lot of photons coming from benzene, great, we know the sample's benzene, right? And if we have a lot of them coming from benzene and no acid, well, whatever. Sorry. Okay. So estimating these rates can help us estimate the concentrations. So here you go. You have the laser. It either hits acetone or it hits benzene. And then the photons come out and they're separated into various bins. And this is actually drawn to scale, this one. So the benzene peak is much higher than the acetone peak. So you got that? That's the game.
Well, there's an overlap in the spectrum, so how do you know when it's from one or the other?
Well, in each individual photon, you don't know, but you collect more than one.
Yeah.
And you look for a pattern. Yeah. So there's three kinds of measurements. You can put a CCD array under the spread of photons and count how many hits each subarray, like a digital camera. Okay, so you can just put a CCD array, and each frequency bin has its own little receptor, blah blah blah. You could put a micromirror array under the spread of photons, and you direct some energies to a counter, and other energies to a sink. Okay, so in that experimental setup here, you put a micromirror away, and you have a detector up here, and some of the photons you bounce up there to the detector, and some of them you bounce away. But now we only have a single detector. CCDs have lots of detectors. We only have one now. Okay, and put a spatial light modulator under the spread of photons, directing a fraction of photons with each energy to a photon count. I happen to have one in my pocket, Ron. I do have a spatial light modulator in my pocket. It's called polarized sunglasses, and I can show you the experiment right now. So I'm going to walk over here. Unfortunately, some people are behind this thing here. This is my generator here. This is my light generator on the screen. And if I put my glasses one way, it blocks all the light. And if I put it the other way, it lets the light through. So these let linear polarized light through in a certain direction and not in the other direction. this one generates linearly polarized light in one direction. So here it's 0. You're letting through 0 of the photons. Here it's 100% or 70%. There's some efficiency. And in between, you're randomly letting them in or not. You're randomly blocking them. Not blocking all of them, not letting all of them through. So this is how a spatial light modulator works.
So your sunglasses are the spatial light.
Well, a lot of little sunglasses, Ron. A lot of little guys wearing sunglasses in this machine. You know, like the Keebler elves or whatever. Okay, you got a question?
I'm wondering if the chirality of molecules you're looking at might have an impact on the distribution of the photon energies and whether you're losing information by selecting out certain.
I happen to know what the word chirality means, but I don't know what the implication is. Okay. So here's how you characterize these. CCD array has many small detectors acting in parallel. A micromirror array or a spatial light modulator sends photons to a single detector, and the pattern of which photon energies are sent to the detector can be considered a filter. Okay, so some energies you send, some energies you don't. Some photons you send. So we're calling that a filter. And this is I didn't know anything about Poisson processes. Okay? But it has amazing properties. Okay, so here's one property. If you randomly assign colors to electrons, according to, that should be photons, according to a fixed probability distribution, then each stream of colored photons is a Poisson process. So if you take a process and you randomly assign colors to these photons, and you look at each color separately, that's another Poisson process. Okay, that's great. If from a Poisson process with rate lambda, you randomly remove counts with fixed probability p, the result is a new Poisson process. This is fantastic with rate lambda 1 minus p. Okay? And if you add two independent Poisson processes with rates lambda 1 and lambda 2, you again get a Poisson process and you just sum the rates. Okay. I claim that each one of these theorems, which is not that hard to prove, matches up with one piece of this equipment. Okay, so here's why. Comes through, you assign arbitrary, you have a probability distribution here of photons, and you're randomly coloring them as you come through. So each one of these things separately is it's a Poisson process. And then from each of these Poisson processes, you randomly remove some fraction of them that you know ahead of time. That means each of them is the Poisson process. And then if you have a micromirror array that sends sums up some of these colors that got through to a detector, now you're summing. So that's the third theorem. Theorem number 1, if you split, you get a Poisson process. Theorem number 2, if you filter, you get a Poisson process. Theorem number 3, if you add them all back up, you get a Poisson process. Okay, so this is cool. This makes the things work out pretty well. Okay. So, what are the noise characteristics of these things? So, if I take this cheap little camera here in my iPod Touch and take a picture and blow it up, you see that there's a fair amount of noise going from pixel to pixel. Right? These little CCD receptors, they act in parallel, but they have what's called read noise. Okay? And it's the same in these chemistry experiments. The read noise has a standard deviation of 8 photon counts. We measured this. Now that's standard deviation, so the variance is 64. So even if you don't have any signal, what you have is a Poisson distribution of counts with mean 8. I mean, that's a lot. I'm going to be talking about things where we count 10 photons total. Okay, so if you have if you have an average noise of 8 at each pixel, you're going to lose. Micromirror array or the spatial light modulator and the photon counter, you can buy a really high quality photon counter for not very much money. It has basically no read noise. It has 200 counts per second. Okay, that's nothing. That's nothing. We're taking milliseconds worth of data or microseconds. So in a low signal environment, micromirror array wins. And you can make it low signal by making it the measurements short. Okay, so what we're interested in here is speed. How quickly can we detect whether it's one chemical or another? So, let's see. So here's the map. I'll tell you the formulation. So this is like a mixing problem. So you mix the chemicals together, and then what you want to do is demix the photons. You want the rates. So here we go. So each column here in this matrix P is a probability distribution. So this is the one for acetone, this is the one for benzene. So the one for acetone will be big here and smaller over here. These all add up to 1. And this is the probability distribution for benzene. This one's going to be the highest of all right there, associated with the blue. And again, they all add up to 1. So it's a normalized spectrum. So P is known. I mean, you can put acetone in the thing and measure it for a second. You'll get 1 million photons. You know what the distribution is. Okay. So lambda is a vector of rate. So lambda 1 might be the rate from acetone, lambda 2 the rate from benzene. Okay, now you multiply the total rates by this probability distribution. That tells you how many things hit the ith energy bin. This is the mixing, right? The ith energy bin, each energy bin gets some photons from the first one and some photons from the second one. And this tells you the probability distribution of that mixing. Okay. And we're going to take m measurements, and we take measurement k for time pkk. So we're going to take m measurements, and we're going to take them for different times. And the times we're going to normalize the sum up to 1. So it might be 1 second, it might be 1 millisecond, it might whatever. They sum up to 1. Different scale. Okay, we're taking. So this filter is this pattern of which mirrors are on and which ones are off. It programs or determines which photons to send to a measurement. So in measurement K, we have a filter, Fk, and the probability of a photon in energy bin 1 being sent along is F1k, and energy bin 2 is F2k, blah, 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 is Fik. So spatial light modulator, it goes from 0 to 1. You can have anything between 0 and 1, okay? You can send energies with probability a half if you want. But for micromirror arrays, it's either 0 or 1. Either you're pointing towards the detector or you're not pointing towards the detector. So those are your options.
Are you going to set this, or you accept what's been set?
No, we're gonna set the mirrors. The mirrors are the thing that we control.
Okay.
And we want to optimally set the mirrors for a certain problem. Excellent. Thank you, Ron, for letting me not pass that up. That's the big thing. How do you set the mirrors? Okay, blah, blah, blah. So here's a little bit. But the columns of the matrix F be the vectors Fk. We normalize this as a diagonal matrix. Some of the diagonal trace is 1. The vector of measurements x hat is independent Poisson. So you take the rates, you mix them, you apply the filters, and then you measure for a certain length of time. P is this diagonal. And lambda hat is we have to go from this x hat here, which is Poisson. Each entry is Poisson with some certain rate. Some certain mean, because Poisson counts now that we're measuring. And so then we let our estimate, lambda hat, be, first we undo the t, and then we have a matrix B here. Now we need to find B too. And this is the blue estimator, I don't know. Best linear unbiased. Unbiased means that the expectation of lambda hat has to be lambda. So this B has to be the inverse of this, a left inverse of this matrix FTP. B is a left inverse of this, and this is the identity. So this is the constraint. So we control F. P is fixed. B is one of these. Best has a particular statistical meaning. So here's the question. How to design filters is best estimate lambda? What does best mean? Okay, so you have to say what best means. So what you're doing is you're choosing the number of measurements. It's not the same as the number of chemicals. The statisticians really know something. The matrix F, you choose the matrix F of transmittance filters, this left inverse B, and then this matrix of measurement times to minimize this. You're minimizing the sum of the variances of the rates. Okay, so that's what you're doing. The sum of the variances of the rates. So that's what optimal means. So this is called A optimality. Okay, so this is what we're doing. Laser, chemicals, filter, aggregate, boom. Okay. So, computational. These are the two most mathematical ones. Computational considerations. This is a non-convex optimization problem on a convex domain. Now, we can optimize it for a fixed lambda. So I call this the design lambda. Okay, we can say if lambda is 100 photons from the first chemical and 100 photons from the second one. I mean, it only depends on the ratio between them. But we can design it to be optimal for that design lambda, and it's good for other lambdas. Okay, it's not optimal for other lambdas, but it's good for other lambdas. Okay, so, and this is the thing. This is the thing you want to minimize. So, you assume you have some lambda bar that's non-zero in all components. You have the distribution P. These things you can choose, and B is the left inverse of F transpose P. And then you can calculate P from this. The statisticians don't look at it this way, but there's some dependence between the variables. Yes?
Sorry, my question is totally remedial, but could you say again how you're indexing the entries of lambda? They're indexed by chemical or they're indexed by spectral, by wavelength?
You're indexed by chemical.
Okay, thanks.
You want to know the rate of each chemical coming up. Yeah. Okay. Now, why is this non-convex? Well, in the standard field of the optimal design, they assume that the variance of each measurement is the same. Okay, so you're taking, the variance is fixed, sigma squared, for every measurement. That's not true here. That's not true because now here it depends on the filter. The more photons you expect to collect in a measurement, the larger the variance. So the standard stuff doesn't quite apply. Okay, and that gives you the non-convexity too. We don't know how to solve the problem efficiently in all cases, and MATLAB does pretty well. you hand it to FMINCOM, you get pretty good numbers. See, really, chemists aren't interested in optimal, right? They just want good. They don't care. Okay. I'm not interested in optimal either. I want good. Okay, so here's some partial theoretical results. We can transform it. Okay, so this was a non-convex problem on a convex domain. We can transform it to a convex optimization problem on a non-convex domain. That doesn't get you much anywhere. We can relax this though. We can look at the convex hull of d tilde, and the optimal solution on this convex hull is the same as the optimal solution to the original problem. But we still don't know how to solve it efficiently, and why is that? That's because you have a few hundred constraints here. You look at this, you have about 100 constraints 200 constraints per filter. I mean, if you have 100 different colors, you have 200 constraints per filter here. And if you have, here's a few hundred more. So there's a few thousand constraints. But once you do this transformation, you have 2 to the 2,000 constraints. That's a different problem, right? So, anyway, so I still don't know how to solve this issue. Okay, this is standard. The statisticians know this. The optimal M, number of measurements, has to be at least the number of chemicals. It has to be full column range. But it might be up to n times n plus 1 over 2. So if you have 20 chemicals, you would have 210 measurements. You take your time, you divide it up into 210 parts, and That's why. Why is this? That's because the covariance matrix is symmetric, or actually the information matrix is symmetric, and the upper diagonal part has n plus 1 over 2 elements, and you have to write it as a product of rank 1, as a sum of rank 1 matrices. So that's why this happened. So some engineers were surprised to hear that. If you have the optimal M, then the optimal filters satisfy Fik is 0 or 1. Okay, so if you know the optimal number of measurements, then you know that micro mirror arrays win. They win. You don't need the spatial. So the statisticians know this too. I mean, once you do this stuff up here, they know that too. So, but like I said, we don't really care about optimal. But it'd be nice. I have to admit. Anyway, but here's something that we can show. If you don't have the optimal M, then the optimal Fk for that M, so you fix the number of measurements. Say you say, I have 3 chemicals, I'm going to take 3 measurements, I'm going to fix them, then the optimal filters can be chosen with at most n-1 components, not equal to 0 or 1. So if you have 2 chemicals, all the filters, you can use micromirror arrays everywhere except maybe one thing, the optimal thing is between 0 and 1. Okay. If you have 3 chemicals, maybe 2 with 100 are between 0 and 1. So we just set them to 0 or 1. That's what we do. Okay. So now we should have some. We want to distinguish benzene from acetone in 30 microseconds. Well, I will say this is an easy problem because these peaks are so differentiated. This is an easy problem. So now these and down here we have a background. In this particular spectroscope, there's this background signal you get, whether there's anything any sample in there or not. So you have to estimate the background. And these gray things are where you set the mirrors. So first you set the mirrors here. It looks like we say it's associated with this chemical. And you do that for about half the time. Then you set the mirrors on here and all the rest are off, and you do that for about 40% of the time. And then you set all these mirrors on and you measure it for only 1.5 microseconds. Okay. So what you measure here in each one of these measurements is about 10 photons max. Okay? About 10 photons max. So the x hat is a vector of measurements. It has 0 to 10 things in it, and it multiplies some vectors, some matrix. So if you think of it as the columns of the matrix, this is going to be on a lattice, right? You have integer linear combinations of the columns of B. So this is going to be on a lattice. So you see this here. You see this here. So this is the lattice. So here we put in pure benzene, and for the really light ones, that indicates 1 count. And we're trying to indicate, this is like Manhattan though, because the darkest one indicates 143 times in 1,000 experiments we had that pair of rates. So this is trying to tell you in 1,000 different experiments, we hit, this was the benzene rate, very high, and 0 for the acetone rate. So this is really benzene, and most of the time you see it gives you 0 for the acetone rate, sometimes something down. This is really acetone, and so that dark dot is 73 times out of 1,000 it was there. So this is like Manhattan too, and then this is the suburbs up here, the little houses. And what I'm doing here is this is a best linear classification, which isn't so good, but this is the best quadratic classifier. And so all these experiments were done, the time was reduced until we get about 1% error, less than 1% error. Okay, so that indicates the sensitivity. And one more example, done. This is true chemical imaging. So what we do here is we have the laser scan the sample. Okay, so this is 300 by 300 image, and you have this laser scanning the sample pretty quickly, and then you take measurements and you correlate it with each dot. So this is 1 millisecond per pixel. So this is 2 sugars that have been jammed together. This is what they look like. in white light. This one has been ground more finely than this one. But you can't really tell apart. If you do 1 millisecond per pixel, this is what you get, okay? So cyan is glucose, yellow is fructose, and if you do 100 microseconds per pixel, this is what you get. So you see there's more noise. There's more noise, but it still looks pretty good. And this measures 30 photons per pixel. So I can tell this sugar from that sugar at 30 photons per pixel. Now I have to admit, this is still an easy problem. If you had different pairs of sugars, it could take up to a few hundred pixels, and then you really have to be sure your laser is aligned correctly and everything, but you can still do it. So what is the moral of this story? Applied mathematicians and chemists need more statistics. And I'm not even a statistician, so there you go.
We have time for a few questions.
Yes.
How much time do you have to repeat the experiment? Because I suppose I get those wavelengths count.
Yeah.
Or
Yeah. Well, here we
what
repeated
should
it.
mean.
Here we repeated it 1,000 times. Okay. Yeah. And here, this one was 1,000 times too.
I have another remedial question and I have a comment that I'll
Okay.
hide in a question. So, when you say that you can that the performance is not monotonic with M, that's because you hold the total acquisition time constant?
No, it is. It probably is monotonic in M. The more measurements you take,
Then why is there an optimal value that's upper bounded by?
well, because the other rank 1 matrices you're adding to get the covariance matrix are 0. Okay, so I mean, if the information matrix has rank 10, then 10 is the optimal number of measurements you take. Whatever the, and I don't know much about Fisher information, but the Fisher information matrix, the rank of that determines blah blah blah.
Okay. And then I'll disguise a comment, but is it correct that the blue here does not necessarily give a non-negative estimate? And so
That's right. Yeah, you can see here. I'm saying that anything below here are negative acetone rates. Anything to the left of here, negative benzene rates.
So what this problem is analogous to what's called multiplex imaging, without throwing away all the chemical aspect of this, just in ordinary optical imaging. This is analogous to multiplex imaging, where actually if you impose a non-negativity constraint, you can greatly improve your performance. It may prevent you from.
That depends on what you're looking for.
Yeah, it may prevent you from proving all these things, but at very low light levels, it can greatly improve the performance to just impose a non-negativity constraint instead of
You
using.
think 10 photons is high light level? No. I know what you're going to talk about. Okay, so I'm an order of magnitude more than you, but it's 10 photons. That's not so bad.
Sure.
Okay.
Any other questions?
Just on the slide, when you set these measurement times, how quick does the mirrors respond?
No, the mirrors take a 30th of a second to respond. But what you do is you set up the filters once, and then you scan the whole image. And then you set up the filters again, 30 milliseconds, you wait until the jitter stops, and you scan the whole image. So this really takes, this over here, I said this takes 90 seconds. It takes 90.1 seconds, because there's 3 filters. This one takes 9.1 seconds. So you only change the filter once, and then you do a complete image scan. That's why you need the equipment really aligned well.
All right, so let's.
Could you say a little bit more about this slide? So, are we seeing different intensities of cyan and yellow,
Yes.
or only different densities? Okay.
No, you're seeing different intensities.
So, what's
So
that
the
mean?
brighter the pixel, the higher the rate. Yeah. So here we have very low rates. I don't know. Anyway, see a little bit of blue here. There's still a few blue pixels there.
All right, so let's thank our speaker. We will meet again at 1 o'clock today for the afternoon session. So if you want to leave your stuff here, room will be closed.